Okay, so the last thing we need to look at before we're ready to run a full hypothesis ANOVA test in Excel is figuring out what the degrees of freedom are for the F statistic. And there are actually two different degrees of freedom, one for the numerator and one for the denominator. And they're fairly easy to calculate, but you do have to know what to calculate. So the degrees of freedom for the numerator of an ANOVA test is calculated by doing k minus 1, where k is the number of groups. Then to find the degrees of freedom of the denominator, you're going to calculate this by n minus k, where k is still the number of groups, but n, capital N, is the sum of the sample sizes for each of the groups. So there's a little work to be done, but it's not hard. It's not difficult. So it says we're going to refer back to question 1 about the 4 groups of 50 patients each in the headache medicine. So we already set up our null and our alternate hypothesis for this one, and we checked all the conditions, and this is just a reminder of the important information that we need for this part. So there were 4 different groups. That tells us k. K is 4 in this case. That's the number of groups. And the 50 patients in each group tells us the n, but we have to actually work for it a little bit. Remember, n is the sum of the sample sizes for each group. So the sum of them would be that there are 50 and 50 and 50 and 50, since there are 4 groups. So there are 200 total people. Now we can find the degrees of freedom for the numerator and for the denominator. So we know that for the numerator, we do k minus 1, so 4 minus 1, or 3. And then to find the degrees of freedom for the denominator, we do n minus k, which is 200 minus, now be careful because k, remember, was 4, or 196 in this case. So you really just have to remember these two small formulas, and then usually you do have to go ahead and calculate that by information given before you go ahead and perform your subtractions. Okay, at this time we have now all of the information to actually use Excel to perform a whole test. And we will be using that data analysis add-in again in order to perform, perform these tests. So here's your ANOVA Excel commands. You're going to load your data. You're going to go to Data, Data Analysis, and there's something called ANOVA Single Factor. You're going to get your input range in. Click your labels in the first row if necessary. Enter the significance level alpha that you're using if necessary. That's usually preset as 0.05, so probably you don't have to do anything there, but you might need to. Click OK. And then you're going to take your F and your P values from that output and interpret them. So not a super hard process, but just more different steps. So here we've got a random sample of people were asked whether they were athletic, moderately athletic, or not athletic at all. And then they were tested for their reaction speed. So shorter distances correspond to a faster reaction time. We want to test the hypothesis that people with different levels of athletic ability have different mean reaction times. And it does say, assume that the populations are normally distributed and have equal variances. So we can check those things off of our list. They are normally distributed. They have equal variances. It says it's a random sample of people, so we're covered there. We do have 3 different groups, so we know we're in that ANOVA setting where we have the 3 different categories. So our input is that categorical variable. And then we're measuring an output of something that's numerical, their reaction times. So this totally fits an ANOVA situation. You want to open this data from the ANOVA data Excel document that I shared with you in Canvas if you want to follow along. The first thing we want to do is go ahead and write our null and alternate hypotheses. So I'm going to just choose one of the versions this time instead of writing them out both ways. I'm just going to pick, to me, the shorter versions. So I'm going to say that the mean, or mu, of the non-athletic group is equal to the mu of the moderately athletic group, which is equal to the mu of the athletic group. And then I'm just going to shorthand it. I'm going to say here, I'm just going to say no association. Kind of as a note to myself to remember that if I'm claiming that all of these mean reaction times are the same, what that's implicating then is that there is no association at all between your athletic ability and your reaction times. Now my alternate is that at least one of these mean reaction times is different. So at least one of these mean reaction times is different. And that would imply that there is an association between athletic ability and reaction time. Okay, now I want to calculate the degrees of freedom for the numerator and the denominator. So let's remind ourselves K is equal to the amount of groups. So in this case, there are 3 groups. And N, we're going to have to work on this. N is the sum of the sample sizes of each group. So I actually have to count all of the data values for each group. If I look down the non-athletic column, I have 1, 2, 3, 4, 5, 6, 7. So there are 7 data points there. In the in the moderate column, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got 7 plus 12 so far. And then in the athletic column, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I take 7 plus 12 plus 10, I get 29. Now, the degrees of freedom of the numerator is equal to, we know, K minus 1. So that's 3 minus 1, or 2. And then there's the degrees of freedom of the denominator, which is N minus K. So 29 minus 3, or 26. Now I'm ready to run that test in Excel. So I'm going to pull my Excel over, and I'll scroll back up so hopefully you can see this, but I think I'm going to have to pull my Excel over the top of it. So I've already got the data loaded, so we're going to go to that data analysis, and then ANOVA single factor is an option. So I'm going to pull this all the way over. And if I go under data, you have to do that first. If you're under home, you see this analyze data, but that's not the same thing. So data, then there's data analysis. ANOVA is going to be your top option. ANOVA single factor is the only one we're doing. Hit OK. Now we have to put our input range. That's going to be all of our data values. So I'm going to make sure that it's already got it highlighted actually, but if not, then you want to highlight all of your data. And notice you have to go from the very top left all the way. You have to make sure you get all of it in that square. I know there are some blank spots in that square, but make sure you highlight everything. Group by columns is fine. Leave that predetermined. I did not choose the labels. If you highlighted the labels when you did this, then choose labels in first row. So you kind of have control over whether you need to do that or not. I don't need to. The alpha value of 0.05 is already listed here. I'm going to keep it as that. And then I just need to click somewhere to be my output range. So you can always click here and then click into that output range area and then click into a cell of where you want to put your information. Click OK. You get a lot of output here. So the first thing I want to draw your attention to, honestly, is the degrees of freedom down here that are listed. Notice that we calculated 2 and 26, but that also can be found in Excel. So just kind of as a note, Those also come out in Excel. Now I need to record the p-value and the f, it says f crit or f critical, oh sorry, not the f critical, that's not what we want. We want just the regular f and the p-value. So I'm going to write that over here, that f equals, let me scoot this back over so we can see. So f is equal in this case to about 0.1041. I'm going to round that to 4 decimal places. And that the p-value is equal to 0.9015. So do be careful there. This F critical is if you were going to do the critical region, rejection region method. You would mark this value and then you would look to see whether your F fell into it or not. But we're just going to do the p-value because that's pretty well used. And then we want to go ahead and give our final conclusion. So that's all I need Excel for. I'm done with Excel. My final conclusion is comparing this p-value to alpha and coming up with my answer. So it looks like since p, this is compared to 0.05, this is way bigger than alpha, the alpha value we're using. So we will reject the null hypothesis. What does that mean? So we're rejecting the idea that all of the means are equal, and we're rejecting the idea that there's no association. So I could say something like, oh, sorry, it's bigger. Please ignore everything I just said, because if p is greater than alpha, we fail to reject the null. I'm so sorry. I can't record the whole video again because I said that wrong. So we are going to fail to reject. What that means is that there is not enough evidence. We failed to reject this, so we did not find enough evidence to say that these reaction times are different or that there is some kind of an association there. So there is not enough evidence to conclude that there is any association between mean reaction time and athletic level. And we could just leave it at that. You don't have to write your conclusions in multiple different ways if you don't want to, but we definitely failed to reject that null in this case, so we did not find any of this evidence of that alternate hypothesis.